Hi, in this video we will see an example of how to detect faces using a classifier. Faces are highly important in our society. They are part of our identity and also a way to communicate emotions. We give them so much importance that the way we identify faces is different from the way we identify other objects. For example, look at this picture. There is something odd about it. But let me show you what happened when we flip it upside down. Now you can clearly see that as humans, we process faces in a holistic way. In other words, we make sense of a face as a set of features that are always together. When we flip the image, we are disrupting the regular processing and our brain starts to look at each individual parts one by one. We can try to take similar approaches in computer vision to identify faces. For example, we can take a bunch of selfies and register them to align them, and now we can calculate the average to create a template of a face, and then search for this template on an image. A better approach will be use principal component analysis. This technique will find what is the most common features of a face and will represent that in the principal component. And we can use this as our target using techniques such as template matching or sift. However, this can be slow if we want to search for many faces of different sizes and in different angles. So the alternative is using something called Haar filters. Haar filters are similar to a convolution kernel, but when we use them combined, we can extract a great amount of information from the image that can be used to train a classifier to detect faces with high accuracy. Here is important to note that if we want to classify faces, we also need to train the classifier with examples of what is not a face. So the Haar filters will provide the same amount of features for every pixel or region of the image that we can use to train the classifier. The other advantage of Haar filters is that they can be computed really fast using something called the integral image. Then we can apply the Haar filters at different scales in short time. So let's see how it works. The integral image is just another image in which each pixel value is the sum of all pixel values above and to the left of the current position. For example, in this position, the integral image is the sum of all these pixels in the original image. If we take this other pixel, the value is the sum of all these pixels. This can be computed in one single pass over the original image using only 4 values. So for each pixel, we can compute the integral image as A equal to B plus C minus D plus A. And we only need to do this once for each new image. Now that we have our integral image, we can apply the Haar filters. So let's take one of the simplest filters as an example. As you can see, this filter looks like an edge detector. So it will give a high value when we place it over a vertical edge. The white part corresponds to 1 and the black part corresponds to -1. So basically, we need to sum all the pixels within the white area and subtract all the pixels in the black area. And here is where the integral image is useful, because let's say that we want to sum all the pixels in this rectangle. Instead of taking each position at the time in the original image, we can take 4 positions of the integral image to obtain the same result. We take the position A, that is the sum of all these pixels, and then we subtract the value of P, that is the value of all these pixels. Then we subtract C, that is the value of all these pixels, and then we add D again, because we subtract this area twice. And we're done. Using only 4 positions, we sum all the pixels in the rectangle. And this does not change with the size. If the rectangle is small or really large, you only need those 4 positions to compute the sum. That is the reason why it's really fast. Now, back to the Haar filter. We have this filter again. So we can see it as 2 rectangles. We start with the white part. We found our corner values and we add them, and then we do the same for the black rectangle. Then we just subtract the black from the white and we are done. We have the Haar value for this particular position. We loop over the image and then we repeat using the rest of the Haar filters. Now we have a vector of Haar features for each pixel. But we don't stop there. We can change the size of the Haar filters to account for scale differences. You can store the result as a matrix or just as a long vector. But now you can train your classifier using these features to detect faces and many other objects in a picture. It is important to notice that if you train your classifier to detect faces as seen from the front, it is really likely that your classifier will fail to find faces when the person is not facing the camera, for example, from one side. This is because the features do not match anymore. In this case, you need to train your classifier with more examples, possibly creating different classes for front faces and profiles. Okay, in this video, we talk about face detection. We review Haar filters and how to compute them to be used in classifiers. See you in the next video.